Okay, so welcome back. This is a continuation in our series, our playlist on understanding transformers. And specifically, we've been talking about how to test a transformer to see if it's got problems or not. And in the previous videos in this series, we've been talking about a testing method for transformers that it seems fairly popular in the hobbyist community, and that is what's called a ring tester. And as you can see here, we've got this natural oscillation, and if we apply a shorted turn, you can see that the response changes, and it goes from maybe a handful of rings to basically no rings. And we talked about this, how hypothetically it's a nice idea, but practically in the real world, we showed that it probably has little or no practical usage to most people for a bunch of reasons. So I encourage you to take a look at the other videos in this series to explain what it is and how it works, and also help you to understand how transformers work. Now in this video, we're going to take the next step and see, well, if a ring tester is of little practical use for a bunch of reasons, what can we do? What's done in the real world to test transformers? And what we're going to look at in this video is just one technique that is used in the real industrial professional world to test very expensive power transformers, and that is called a sweep frequency response analysis. What is a sweep frequency response analysis, also called SFRA? Well, as you can probably imagine from the name, it looks at the response of the transformer as you sweep the frequency, the applied frequency to the winding, and it takes advantage of the fact that this is a fairly complex RLC circuit, and as you sweep the input frequency, the impedance will change as the inductive and capacitive values of this very complicated winding change. So let's take a look at what an SFRA test is. And again, it's just one technique that is used in the professional world to measure transformers. There's also TTR tests, which are called transformer turns ratio tests. And there's a bunch of other techniques. We're just going to look at this one SFRA test to help us understand a little bit better how transformers work. So let's take a look at the very basics. We're going to go into LT Spice and make a very simple model and show you what the SFRA technique does and how it might help us. So here we are in LT Spice, and again, if you haven't used LT Spice, I encourage you to look at our series LT Spice from Beginner to Expert that shows you how to use this free software, and it's really wonderful if you're learning electronics or you are building circuits and you want to test them to see how they respond before you build them on the bench. It's a wonderful way to learn electronics and electrical stuff. In LT Spice, we have here a very simple circuit. I've got a source, which is a sine wave. I've got a simplified model of a single transformer winding, and then I've got an output resistance. So what does this SFRA test do? Well, in the simplest form, you basically have your sine wave that you are applying to your transformer winding, and we've got the winding in series. So here is, in our case, our 117 volt power transformer winding. And here are the two input terminals, and I've got this connected in series with an output resistor. And the way the SFRA test works is you vary the frequency of this input voltage and measure the output voltage as that frequency varies. Now, why would that output voltage change? Well, in our very simplified model, you know that with this inductance, it's impedance of this inductance varies with frequency. And if you look up here, the inductive reactance of an inductor is this constant 2 times pi times whatever frequency you apply times the inductance. Now the inductance is constant, the 6.28 is constant, so as you change the frequency, the inductive reactance is going to change, which means that this kind of voltage divider here, the output voltage will get less as this inductive reactance increases. With a high frequency, we're going to have a big inductive reactance here, and that means the output voltage is going to drop. So with this very simple model, you can see that if I change the frequency of this voltage source, the output voltage magnitude will change. So now let's take the next step and see how we would hook that up with our existing ATX power supply switching transformer and how this SFRA would work. So we've got our input voltage source, and you can see we're doing an AC analysis. Again, we've got a video in LT Spice how to do an AC or frequency response analysis. And we're going from 10 hertz to 10 megahertz. And we've got the output resistance of this function generator we're going to use. And we have our transformer. We measured the series resistance, about 0.5 ohm for the windings, and then 6 millihenries of inductance. And then we have this output resistor to match the output impedance of the function generator. And we're going to be measuring the voltage across this output resistor and see how it changes as we vary this frequency. And here we've got our two output windings that are disconnected for now. So let's run this simulation and see what the results are of this output voltage. And here is the result. You can see we've got from 10 hertz down here on the bottom left to 10 megahertz. And the output voltage, and it starts at about 10 volts at low frequencies, and as the frequency increases, you can see around 10 kilohertz, it's here, and then it gets almost down to 0 as the frequency goes way up, which means this inductive reactance goes way up, which means the output voltage drops down to almost 0. So this is the basic concept behind a sweep frequency analysis. And the idea is if we take this transformer as a new transformer, we can run this analysis, and this becomes kind of a fingerprint for a known good transformer that in the future, if we do the same analysis, we should get a frequency response that looks like this. And that's basically what an SFRA analysis does. However, the model we have here is a vastly oversimplified model if you're talking about high frequencies like this. In fact, there's a lot of capacitance in this transformer. Each winding, between the windings is a capacitance, which means there's, for hundreds of turns, you've got hundreds of little capacitors. You've got capacitance from the windings to the iron core. So a transformer model is really, really very complicated. So the actual SFRA fingerprint for a particular transformer is probably going to look quite a bit different. So let's take a look at what that might look like with a more realistic transformer model. So here what I've done is I've made a slightly more complicated, though again very simplified model of our transformer. I've broken our series inductance into separate values, and I've put capacitors across those separate pieces of windings and some capacitance to ground. Again, this is not going to be accurate, but it's just to give you an idea of how complex an actual transformer model has to be if you're going to vary frequencies. So let's run this and see what we get for an output. Here is, we've done a frequency response, and we've also done a step. I've also varied a resistive value here across one of the windings to kind of sort of simulate a shorted turn. Again, it's not going to be accurate, but at least it gives you an idea about what a real SFRA frequency response might look like. And here we have from 10 hertz to 10 megahertz, and you can see the impedance changes a lot, which means this output voltage that we're measuring is going to change with frequency. And if you have, for example, a resistance of a shorted turn, you might see a big spike or a big change from what you got without that. So this is the basic concept behind an SFRA test. So now what I've done is I've gone back to the bench and I've applied that test circuit where I vary the frequency of the applied source voltage to our switching ATX power supply transformer. And I've done it with and without a single shorted turn. And I've gone through, you can see I've varied the frequency over here. It's quite a bit of work if you have to do it manually. But I've gone through and varied from 10 hertz up to 10 megahertz and measured that output voltage. And in the orange trace, I've got the results of the output voltage with one shorted turn. and without a shorted turn is in blue. And you can see there's a significant difference between the SFRA results. Now, is that going to help you? Well, maybe, maybe not. Depends on the transformer, and it kind of relies on you having a good transformer fingerprint so that in the future, if you do have a problem, you can compare them to see what's good and what's bad. Here is the same test, but instead of using the switching transformer, I used my 117 volt to 12 volt power transformer. And you can see the SFRA test looks kind of similar with and without shorted turns. And you can see up at the high frequencies, we get a big spike in the impedance as we get a resonance with the L and C. So again, is it going to help you with your particular transformer? In the real world with very expensive power transformers, it can be quite useful. Let's take a look at a typical large power transformer SFRA test result to see what the difference is. So now here is an example of the results of an SFRA test for a very expensive, very large power transformer that might be used by your power company to feed electricity to your house or office. And this is for the 3 windings of a 3-phase power transformer. And we're going from about 20 hertz up to about 2 megahertz. And you can see that it's kind of like what we saw, except there's quite a bit more variation. And that's due to the fact that the transformer itself is, like we said, very complicated. There's a lot of inductances, a lot of capacitance inside the transformer that interact. You can see each of these little peaks and valleys are the result of the interaction between the inductance and the capacitance, causing a variation in the overall impedance of that winding. You can see we've got 3 windings, a red, green, and blue on top of each other, and even with different windings, you can see there's quite a bit of variation. But you can imagine that this would be kind of supplied by the manufacturer upon building the new known good transformer, and then in later years, the utility or the industrial customer can perform a similar test to see if any of this changes, and that might be a good indication of a problem with the transformer. So again, that's one way to measure how good a transformer is. There's many different ways to do it, and what applies for your particular needs can vary quite a bit. So you need to really be knowledgeable about these tests and what is really going to be of use and what isn't. So that's about it for the SFRA. If you're liking these videos, hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Otherwise, take care. Have a really good day. Thanks.